Have you ever wondered how your brain stores all the information you learn every day? Picture this. You're memorizing a new recipe for dinner or learning to drive a car for the first time. These activities, seemingly simple, are powered by an extraordinary process taking place within your brain. This process, known as learning, is more than just the acquisition of new information. It's the brain's ability to change and adapt, to form new connections and strengthen existing ones based on the experiences we encounter. And what about memory? Think of it as the brain's personal library, a place where all learned information is stored and retrieved when needed. It's these two fundamental processes, learning and memory, that allow us to navigate our world, to grow, to adapt. But how exactly does our brain do all this? Much more than just a storage unit, our brain is a complex system that constantly changes and adapts. Let's dive deeper into how it all works. Think of your brain as a city, with neurons as the buildings and synapses as the roads connecting them. In this bustling city of ours, neurons are the fundamental structures, the skyscrapers, houses, and offices. They are the basic units of the brain, with each one having a unique role in processing and transmitting information. There are approximately 86 billion neurons in the human brain, each one buzzing with activity, contributing to the city's vibrant life. Now, a city wouldn't function very well if its buildings were all isolated, would it? This is where synapses come in. If neurons are the buildings, synapses are the intricate network of roads, highways, and bridges connecting them. They allow information to flow from one neuron to another, facilitating communication and collaboration. Without synapses, our brain city would be a chaotic mess, with no information getting where it needs to go. But here's where things get really interesting. In our city analogy, you might imagine these roads as static, unchanging, but they're not. Synapses, much like a city's infrastructure, can change and adapt. This ability to change is what we call synaptic plasticity. Synaptic plasticity is the brain's ability to strengthen or weaken the connections between neurons, the roads in our city. If a specific route is frequently used, the connection becomes stronger, like a small road evolving into a bustling highway. Conversely, if a route is rarely used, it may become a quiet side street, or even be closed off completely. This is a continuous process, happening every second of every day. It's influenced by everything we do, every thought we have, every new thing we learn. It's the basis of how we form memories and acquire new skills. So with every new thing we learn, our brain's cityscape changes, with roads, synapses, becoming wider or narrower. But how exactly does this happen? Stay tuned to find out. Here's where the magic happens: synaptic plasticity. Let's break it down. Synaptic plasticity is the ability of synapses, the gaps between neurons, to strengthen or weaken over time. It's like a workout for your brain. The more you use certain neural pathways, the stronger they become. On the flip side, if you stop using these pathways, they will gradually weaken. There are two main mechanisms of synaptic plasticity: long-term potentiation and long-term depression. Despite what their names might suggest, these terms have nothing to do with mood disorders. Long-term potentiation, or LTP for short, is the strengthening of synapses. This is the process that happens when you practice something, like playing the guitar. The synapses involved in playing guitar will strengthen as you practice, making it easier for the signals to travel along these pathways. On the other hand, long-term depression, or LTD, is the weakening of synapses. This happens when you stop practicing a skill. The synapses involved in this skill will weaken, making it harder for signals to travel along these pathways. Consider, for instance, learning how to juggle. When you first start, the synapses involved in juggling are weak because you've never done it before. This is an example of long-term depression. But as you practice juggling, the synapses involved in this skill strengthen. You're essentially building a stronger neural pathway for juggling, thanks to long-term potentiation. Through these two mechanisms, our brains can adapt and change based on our experiences. This is the essence of learning, the ability to modify our neural networks based on new information. It's a constant process of strengthening and weakening, building and breaking, learning and unlearning. So, by changing the strength of our synapses, we are effectively learning and storing new information. But is that all there is to synaptic plasticity? Stay tuned to find out more in the next scene. Synaptic plasticity doesn't just help us learn new skills, it's also the key to forming memories. Now, let's delve into how this fascinating process contributes to memory formation. Imagine you've just returned from an unforgettable vacation. Every time you recall that trip, your brain revisits the synapses that were fired during those experiences. Each revisit or recall strengthens these synaptic connections. It's as if your brain is saying, this connection is important, I'll make it stronger. This reinforcement makes the memory of your vacation more vivid and easier to recall. The same principle applies to all memories. For instance, if you've ever crammed for an exam, you'll know that repeatedly going over the same material helps cement it in your memory. This is your brain's synaptic plasticity at work, strengthening the connections between neurons that are repeatedly fired together. In essence, synaptic plasticity is like a gardener tending to a garden. The gardener waters the plants that need to grow, just like our brain strengthens the synapses that need to become more robust. Over time, with careful nurturing, the garden flourishes. Similarly, with repeated use, our memories grow stronger and more vivid. But what about the memories we'd rather forget, or those that fade over time? Well, synaptic plasticity has a role here too. Just as a gardener might prune back overgrown plants, our brains can weaken or even remove synaptic connections that are no longer needed or used. This process, known as synaptic pruning, helps keep our neural networks efficient and focused on what's important. So, in essence, synaptic plasticity is the brain's way of prioritizing and managing information. It strengthens the connections that are used often and weakens those that aren't, helping us form, recall, and even forget memories. So, thanks to synaptic plasticity, not only can we learn new skills, but we can also form and recall memories. But what happens when things go wrong? Unfortunately, not all brains can adjust their cityscape as easily. In some cases, the process of synaptic plasticity may not function as it should, leading to a variety of learning disorders. Imagine the brain as a bustling city, with neurons as buildings and synapses as roads connecting them. In a well-functioning city, the roads are constantly adjusted based on traffic patterns. Some roads are widened to accommodate more traffic, while others are closed off if they're not used. This is akin to synaptic plasticity, where the connections between neurons strengthen or weaken based on use. However, in some cities, the road management system may not work properly. Some roads may remain narrow despite heavy traffic, causing congestion, while others may be unnecessarily wide, wasting resources. Similarly, in cases of learning disorders, the synapses might not strengthen or weaken as they should. This can make it challenging for the individual to learn new information or recall memories. For instance, in dyslexia, a common learning disorder that affects reading and language-based processing skills, the brain may struggle to strengthen the synapses associated with linguistic processing. This makes it difficult for individuals with dyslexia to recognize and process phonemes, the smallest units of sound that can distinguish one word from another. In another learning disorder, ADHD or attention deficit hyperactivity disorder, the brain may have difficulty weakening unnecessary synapses, leading to an overload of information. This can result in symptoms like inattention, hyperactivity, and impulsivity as the individual struggles to filter out irrelevant information. These are just two examples of how disruptions in synaptic plasticity can lead to learning disorders. Each disorder has its unique set of challenges and requires a tailored approach for treatment and management. Understanding synaptic plasticity is not only fascinating, it's also crucial for developing treatments for learning disorders. Remember, every time you learn something new, you're reshaping the cityscape of your brain. Our brains are remarkable, aren't they? They are like bustling cities, with neurons as buildings and synapses as the roads. Memory and learning, the lifeblood of these cities, are made possible by the busy work of these structural elements. These functions of the brain, as we've seen, are not static but dynamic, constantly changing, growing, and adapting. At the heart of this change is synaptic plasticity, the brain's ability to strengthen, weaken, sprout, reroute, and prune its synaptic connections. This flexibility allows our brains to store new memories and learn new skills, making our cerebral cities ever-evolving landscapes. But just as cities can face challenges, so too can our brains. Understanding the role of synaptic plasticity in learning disorders provides us with valuable insights to navigate these